This video is designed to serve as your introduction to the topic of sequences and series, which is going to be our next focus in standard level mathematics. Sequences and series are very much rooted in the idea of patterning, but at the same time do have some connection back to functions, which we've been exploring up until this point. And so to kind of launch into this topic, I feel it's best to just sort of start with a sequence. So when we talk about a sequence in math, we're talking about a list of numbers. So here's a list of numbers. I'm basically starting with 1, and then each subsequent number in the sequence has increased by 3 from the previous one. So 1 plus 3 gets me to 4, 4 plus 3 to 7, 7 plus 3 to 10, and so on. Now, if I continue to write out a list based on this rule, I could keep on going forever. If I'm adding 3 each time to get the next entry in the list, it's going to go on indefinitely. So there are many sequences that would progress infinitely. And so writing out a list explicitly, including every entry, really doesn't end up being feasible. So where we kind of start our discussion of sequences is actually looking at how do we go about expressing that list in a way that can be more concise, or a different way that allows us to look at that information perhaps from a different perspective. And there's a lot of ways in which this can happen. This sequence, if you had ever looked at it in earlier grades, you probably would have actually started by focusing on a pictographic representation, because that tends to be a pretty hands-on way of envisioning a sequence. So here I'm actually drawing out the entries in this sequence, and I'm doing it as a picture. So in this first image, I have only a single dot. And then in the next image, I've added this column of 3 there to make 4 dots. And I've added another column of 3 here, which brings us up to 7, and another column of 3 here, which brings us up to 10. Representing it as a picture makes it perhaps a little bit easier to grasp, but it doesn't fix that problem of acknowledging that this will go on forever. And so if I want to actually be able to come up with a way of referring to a sequence that's more compact and will allow me to look at a sequence that goes on for many, many terms or infinitely, a picture's not really going to cut it. And so sort of the next step then maybe comes down to the notion of writing out a description. I could legitimately say that this is a sequence that starts at 1 and goes up by 3, or increases by 3. You add 3 each time. There's a lot of different ways you could describe it in words, but that's sort of a general way of summing up that sequence in a sentence. And so that's fairly concise. The rule's established. I know my starting condition. I know how it's going to change each time. But that still isn't the optimal mathematical way of describing a sequence. There's nothing I can do with this. It has some numerical components, but there's no way I can really dig into this and have a nice, robust, analytical way of exploring this. So basically what we do with sequences is we say, okay, if this is a list, we need to start introducing some notation and some vocabulary around how this list can be expressed. And so I'm basically going to take that list, and instead of just writing out the entries in the list, I am also going to write out their position in the list. So above them, I'm just going to write out their position and circle it. So that's position 1, 2, 3, 4. If I was to continue the sequence, and I'm going up by 3 each time, my next item in the list would be 13, and that's in the 5th position of the list. And then 16 would be the one that follows, and that's in the 6th position in the list, and so on. So this is now giving me a way of referring to the position in the list, and then also knowing what's in that position. And so then it comes down to really connecting the two. So the vocabulary we kind of use around a sequence is we refer to each of these items in the list as terms in the list. And so this number here that is telling me the position, we would then call the term number. So if I asked you what's the first term in this sequence, you would say 1. If I asked you what's the fifth term in this sequence, you would tell me 13. And so now we start to build some vocabulary around the idea of sequences. And so then the next step for any sort of mathematical generalization is to come up with notation that surrounds this vocabulary that we have. So basically what we do is we define the term number. We tend to generalize it as n. And so I'm going to actually rewrite this sequence now into a table and say when n is 1, I know that the value of that term is 1. When n is 2, the value of that term is 4. When n is 3, it's 7, and so on. I'm just copying all that stuff down from above, migrating it down into this table. And so then as far as referring to the actual terms themselves, the notation we tend to use, and it varies. You can use any sort of variable that you want. But when we're talking about sequences and series, we tend to use a variable that indicates that something is a term. And then what we actually do is we put a subscript on it. So the preferred notation with the IB, they use the letter U to indicate a term in the sequence with a subscript of n, and that's going to indicate its position. So for example, 1 would be written as U1. That's the first term of the sequence. And 4 is U2. 7 is U3, and so on. And this is how we would actually designate these items in their various positions of the sequence. But again, we do still have this problem that this goes on indefinitely. I start with the first term in a sequence, but I can keep counting upward. There are infinitely many natural numbers, and so there will be infinitely many items potentially in a sequence. So it really comes down to now, how do we take this information? We took it from being in a list to expressing it in a table, and how do we take that information and really generalize it? And so if you're looking at the table and thinking, okay, this is starting to feel like just a table of values, maybe like an x and a y, perhaps we can just come up with a general equation. That would be a good instinct, and that's exactly what we're going to do with this sequence. If I look at this as being sort of an x and a y value, the fact that this is going up by 3 really almost suggests that this is linear in nature, right? It increasing by 3 each time is the equivalent of the slope of a line. And so I could technically generalize this with the equation 3n. Now, that's going to be my starting point because it's changing by 3 each time. Obviously, 3n doesn't work on its own as a pattern. If I put in 1, it says my first term should be 3. So I'm going to think about, okay, what's the y-intercept have to be in order to get me to that point 1? And I'm going to say that it would have to be minus 2. So I get 3n minus 2 is my general rule for this pattern. You can see now that if I were to substitute 1 in as an n value, I'm going to get 1 back as the term value. If I put in 2, I get 6 minus 2. That gives me 4. So this becomes what we would call general term of this sequence. Which is basically just a way of saying this is a general formula that for any value of n is going to give me something that's in the sequence. And so I'm going to actually write the general term out like this. I'll say that un is equal to 3n minus 2. That's the term that is used to generate this sequence. And in a lot of ways, it is really pretty much just a function. I mean, I could have realistically, and this is not the notation that we will use, but I could have realistically said that this is a function f, and the variable is n, and the equation then is 3n minus 2. I could have defined it that way. I would have had to be very careful in the context of it being a sequence in just leaving it as is, though. And there's even a reason why I've used n as the variable instead of x. We're used to functions that are expressed with an x, and then typically we're operating within the domain of all the real numbers. But sequences that we're talking about are lists, and the lists have numerical positions, countable numerical positions, the first position, the second, the third, the fourth, and so on. And so our domain for this equation isn't the real numbers anymore. We're actually operating so that n is an element of the natural numbers, not the real numbers. right? N is taking these values 1, 2, 3, 4. It's the countable numbers. We don't have n equal to 0. We don't have n going into the negatives. We don't have any decimals or fractions or anything like that. We're strictly speaking dealing in the natural numbers. Or another way, I guess, of writing it would be that we're dealing in not all the integers, but certainly the positive integers. And so that's what actually makes sequences and series fall into this unit that I've called discrete functions. The word discrete means that something is countable, that it's not continuous. So continuous quantities we would measure, and so every function that we've been looking at before this has been a continuous function. We've been able to put in any x value that you could realistically measure, so you'd always be able to get more precise decimals. But this is a discrete function. It only works for countable numbers because there's a first position, a second position. There's no 1.5 term in this list, right? If I'm listing things out, there's a first item, there's a second item, and there is nothing in between. And so that's what makes these functions different, and it is why we tend to distinguish them with this notation rather than using function notation. But having said that, it is, for all intents and purposes, a function. It's just a different way of expressing a function. It's on a different domain, but really it is just a different type of function. You can really see the difference if you go to graph it. Because if I graph 3n minus 2 as a function, and its domain is the real numbers, what I end up with is this line where I have a y-intercept of minus 2 and a slope of 3, and so it ends up looking something like this, right? If I'm graphing a discrete function, though, what I have is items in the first, second, third, fourth position, and when I go to start graphing a discrete function, and I'll do this one in particular, what I end up with is actually just solitary points. So I have a point at 1, 1, because the item in position 1 of my list is a 1. I have another point here at 2, 4, because in the second position I have the number 4. And I would keep going up to 7. I'll have 3, 7. It's still following the trajectory of that line, but there is nothing in between those points. When we're talking discrete functions, we just have these items that kind of sit in isolation. And so the way we try to distinguish that, and again, all of mathematics is pretty intricately connected, so discrete functions are functions. A lot of the rules we've talked about for functions work for discrete functions in the same way they work for anything else. We could have discussions of domain and of range and all of that, but because it is kind of a distinct subset of functions, we do use this different notation. In fact, because I don't ever want to refer to a discrete function as a function f of n, typically, the way we actually would represent a sequence, instead of using f or g or some name of a function like that, what we do is we take that general term and we put it in these braces, or what some people refer to as curly brackets, and this is actually how we would express a sequence. So we wouldn't give it a name, we wouldn't assign it with function notation, we would write the sequence in these braces, and inside the braces we put that general term. That's the term we use to generate the sequence in question. So if I just decided to make up an arbitrary new sequence that I want to look at, so let's say I'm going to look at the sequence n squared, which would be a sequence of perfect squares. This sequence, if I was to write it out, would be written as 1, which is 1 squared, and then I'd have 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, and so on with all of the perfect squares. And again, that goes on forever, so this sequence would be infinite. But that's the sequence of numbers that's generated by that rule. And you can make up all sorts of rules. I mean, you could have the sequence 1 over n, and what that would look like is you'd have 1, because that's just 1 over 1, but then your next item in the sequence would be 1/2, and then 1/3, and then 1/4, and 1/5, and so on. Right? And that would be another example of a sequence. And so you can really come up with any sort of rule to generate a sequence. It could be based on multiplying things together or adding something every time. There's a wide variety. We're going to look at very specific sequences over time and talk about how to generalize sequences where the rule is based on addition, so adding something for each term, or multiplying something for each term. That's going to be sort of the standard that we look at. But there's obviously a wide variety. This sequence of perfect squares is not one where I'm adding something constant each time. The idea is I'm taking the term number and I'm squaring it, and that's how I get the items in the sequence. This 1 over n is basically the reciprocal of all the natural numbers, so that's how I get the items in that sequence. You have likely even seen other sequences or presumably been exposed to other sequences, because there's one famous one that almost everybody knows, and when you talk about a mathematical sequence, this one tends to come up most often, and that would be the Fibonacci sequence. Now this is a really special sequence because of how it's defined. The rule for this sequence, where I've written out the first few terms there, the rule for this sequence is actually not one where it's very easy to come up with a general equation. See, there's no consistent thing that's being added here. There's no formula that I can just pop something into and get 2 for one value and 3 for another and 5. Right, these are all in different positions. This number's in position 1, this one's in position 2, 3, and so on. But there's no formula that I can come up with that will explicitly define this sequence. And that's because this Fibonacci sequence, which is oh so famous, is famous for a reason. It is what's called a recursive sequence. And so a recursive sequence is one that is actually built upon itself. And so if you look at the terms of the Fibonacci sequence, the first 2 terms are both 1s, and the third term is a 2. And the rule that's used to generate the Fibonacci sequence is actually that each term, starting from the third and moving on, is the sum of the 2 previous terms. So when I do 1 plus 1, I get 2. When I do 1 plus 2, that gets me 3. 2 plus 3 gets me 5. 3 plus 5 gets me 8, and so on. And so that's how the Fibonacci sequence is generated. It's taking the 2 previous terms in the sequence and adding them up. So that's recursive, but because it references the previous terms, there's really no way for me to come up with an explicit formula. This is actually one where you would have to define it using function notation, or you would have to define it kind of self-referentially. So I could define a term in the Fibonacci sequence by saying that any new term is going to be the sum of the term that came immediately before it. So the nth term would have to take the n minus 1th term, that's the one immediately before it, and the one that is 2 before it, so n minus 2. So I can write it out this way, and this gives me a recursive definition. It says I need to know the previous 2 terms in order to get the next one. And we have to kind of define some initial conditions where the first term is 1 and so is the second term. But then that would give me a suitable definition or way of expressing the Fibonacci sequence as a recursive sequence. So you start off with those terms. Term 1 is 1, term 2 is 1, and then you just start adding them together to generate other things in the sequence. Using function notation like I showed you before, you could technically have written it as fn is equal to f at n minus 1 plus f at n minus 2. But again, that's not a notation we'll use too commonly. We do tend to stick to the un and various other subscripts as we go along. So that's how you would represent a recursive sequence. Now, within the scope of our course, with SL Mathematics, we don't tend to focus too much on recursive sequences. I just find, as a point of intellectual curiosity, recursive sequences are really interesting to look at. Anyone who's studying DP computer science has some sort of exposure to the notion of recursion, because when you're looking at things like loops, that's sort of a recursive process and getting something to go back and reference itself repeatedly. And so it is still an idea that even though we're not going to do a lot of really comprehensive problem solving with it in the scope of our syllabus, it is still something that might have connections to other areas that you're studying. And honestly, it's just really interesting. The Fibonacci sequence, as it's defined here, starting with two ones and building on itself, is actually just one type of recursive sequence. You could actually change those first two terms to be anything you like and sort of come up with your own recursive Fibonacci-like sequence that builds on the previous terms, but is going to give you different numbers depending on what you start with. If I decided my first two terms are 1 and 2, the sequence is going to build in a slightly different way than it would have otherwise. Anyway, the Fibonacci sequence being recursive is one type of possible sequence. And you can, again, as I said, define any rule to govern a sequence that you like. There's a lot of really interesting ones that we will look at, and a lot of really interesting problems we will solve using some of the more common sequences. So we will look at sequences that are called arithmetic sequences and geometric sequences, and kind of just look at the patterns that are built into those things, and then start to really talk about the applications to problem solving that these have. So the main focus on discrete functions is actually getting a much richer understanding of these patterns, how we connect those ideas of patterning back to functions, because again, by being able to come up with explicit formulas for things, which does connect back to all of the work we've done on functions up until now, coming up with explicit formulas allows us to better generalize things, which then allows us to solve other problems. It allows us to prove certain things. And so there's a lot of potential to be had by exploring some numerical sequences in a very, very clear way. And so that's going to be our focus for this next unit. We're going to actually do a lot of patterning-based work and developing that kind of thing, which kind of draws upon the Criterion B investigating work that you would have done in MYP. This is sort of the natural extension of that. So if you're thinking, where's the unit where that's going to come up the most, this is one of the bigger sources of that kind of patterning and investigation and journey of discovery into these kinds of things. This is where you're going to see a lot of those skills make a resurgence. And so this is where I'm going to kind of leave it for now, because to have a really robust discussion about specific types of sequences, I feel like that is better served in person. Plus, I want to make sure that you have the opportunity to get familiar with the notation and working through kind of generating some sequences on your own. So there are some exercises to be done from the textbook. A lot of the work for sequences and series is coming from book 1, so please make sure that you're bringing that with you. It's only the last topic of this unit where we'll actually go back to book 2. It's just how the publisher split things up in the new iteration of the book. But most of the stuff that you'll need will be in book 1. So there's a lot of good exercises in there that will have you coming up with descriptions for sequences and general rules. It's really important that you feel like you're sort of fluent in the language of sequences and series, because we'll kind of ramp up into a bunch of different contexts fairly quickly. And I do want to make sure that everyone has a certain degree of fluency before we get into the really challenging problem-solving stuff. So that's where I'll leave it for now. I know I've been talking in a pretty steady stream, but the benefit of this being in a video is that you don't have to keep up with me talking. Hopefully you have either paused or now feel comfortable going back and rewinding, watching certain sections again to make sure you've got a good understanding and a comprehensive note here. And when we see each other again, we're going to start into those arithmetic sequences and do a bit of a deeper dive into what sequences look like and how we can kind of generate them and solve some problems with them. So that's where I will leave it for now, and I will see you all